molto onorato di... È un onore per me ricevere questo premio così prestigioso, anche visto i numerosi messaggi che sono arrivati di congratulazioni, quindi questo premio sta prendendo piede e sono molto felice di essere anche nel novero di quelli che hanno ricevuto questo premio, che comprende anche Enrico Presulti o Jean-Jacques Marigot, che sono tutte persone che mi hanno influenzato direttamente, che io vedo come esempi, quindi sono molto felice di essere in questo evento. Anche felice di avere il nome legato a quello di Giulio Levi-Civita, che è un mio lontano parente matematico, diciamo, che ho visto nella genealogia, che è il suo bisnonno matematico e il mio quadrisnonno. Sedini, siamo in famiglia. Forse c'è qualcuno nell'audience che non parla italiano, quindi magari la conferenza, il seminario lo farà in inglese. I thought this would be a good occasion to describe what we have been doing in the last 15 years or so. Something started with Roberto Nicandro and Maristella Gelli way back when I was in Sissa, so before coming to Rome. And since then has involved a lot of people, a lot of interactions that by chance involved different standpoints of the same problem at the same time. It's something that happens quite often in mathematics. People are not thinking of some problem, and immediately at some point from different locations, different backgrounds, they're thinking about the same thing. So I will illustrate the work of the people in red. A lot of other people were involved directly in connecting these results or interacting with us. And there is another list there, more in that. So, this, as was mentioned, my research is linked to applications, and my interest came from applications, and this is a list of applications. Again, in a sense, it's in chronological order as my interest was concerned. So first, we started with numerical analysis and discrete systems. In numerical analysis meant finite difference, finite elements, and it was something really sounding dull way back in the 80s. From the standpoint of variational convergence, it seemed to be a problem of rate of convergences and not very, very exciting. The excitement came in the 90s when we started looking at computer vision models, where you have non-convexity, which is important in the problem, really makes a difference in the models. And we realized then that it was linked to atomistic modeling. So against other problems where the potential were not convex concave potential like in arbitrary convex concave potential like the one in computer vision, but were already given potential like Lennard-Jones ones. So this is a development of the interest in time that carried from a numerical analysis to atomistic modeling. Now we have other applications which I summarize in some pictures, like the design of lattice structures, which are really big now, or the study of optimality properties of biological tissues like viruses. There will be a seminar of Braides here in some time. Or control of traffic causal networks, and or other applications. So in all these problems, a common feature is that we have a lattice reference. So what I'm going to talk about today is networks, so systems where you have a lattice and you have interaction between the points of the lattice. So this can be a geometric design constraint because we are looking directly at nodes of a traffic network, for example, or it's justified by the fact that we are maybe close to equilibrium, it's some physical system and some crystallization of it. And I am a variationalist, as I was labeled before, so I will be in a variational setting. I will have an energy which I think will drive my system. The easiest type of energy that you can think of is pair interaction. So if every pair of points, every pair of nodes in the lattice interact among each other, and then the total energy is a sum of all these interactions. And usually this interaction depends really on the difference of the values of the sides, which they value some Rn, so this is a distance. So something depending on the distance is pretty common. And the overall environment, mathematical environment, is that of discrete-to-continuum analysis, meaning that we are looking at systems where we have an increasing number of nodes, and we are looking at having an overall continuum theory that describes what happens to the system without resolving the single interaction of the nodes. And this is done not at examining larger and larger samples, but instead scaling everything to a single domain. And this is done by introducing a scale parameter. So instead of looking at a fixed lattice, we scale the lattice, introducing a small parameter. So we're thinking we have a small lattice and then we are magnifying it rather. Then we scale the energies. So this is an important point because different scaling will bring different type of outcome. But we have, of course, it's not arbitrary. From the scale energies, we have to derive the behavior of the unscaled functions. And then we have to define a continuum parameter. So meaning that we have to define a convergence of these discrete functions defined on these discrete sets, discrete lattices that are a scale of a common lattice. And this convergence usually is just a convergence of interpolations, but not always so. So somehow also this is a part of the game. And then we have to define the effective problem. And the effective problem is something more rather abstract at this point. It's something that so that if we solve the effective problem in the limit, then we have some information on the solutions at fixed epsilon. So that's the important thing. So we want to know something about the epsilon fixed problem and the approximate with a continuum. I'd say that this is a very, very complex problem because this is a very, very bad transparency. You don't have to read it. You don't have to read it. It just means that, okay, even if you take very simple interaction, like quadratic interactions, if you scale them differently, so even if you take just the same interactions, suppose this is a quadratic interaction, then you scale it, scale either the function or the energy different, then you obtain completely different outcome, which can be, we can describe as statistic, or the oscillations, or the surface energies, or the vortex appearing, and all of them come from the single energy. So in general, we will have a superposition of all such description, and it's a major issue then to put together all the description different scaling in one big theory. And that also stimulates some discussion with that Spinoza, but I'm not going to talk about it. So, but saying that, okay, the outcome can depend on the way we scale the energies, and a major problem is putting back the different type of analysis together. So, my talk about, after this introduction will be about 3 points. One, that okay, as it was mentioned, I'm part of a big school coming from the Georgie, and within the variational theories of the Georgies, we have developed a lot of methods on the continuum, which can be exported on the discrete setting. So the first part will be to see that we were careful, and the Georgian premise was careful, to define all the theories in the most flexible way, and with some adaptation they can be adapted to this passive discrete continuum. But then the second point is that we are solving different problems, and it's the interesting issue. Because the discrete nature brings different type of parameters which we can play with, so we have more effects, and we can either simplify the models, derive the theories that are usually studied and seeked after the continuum, and simpler answer. But then we have other types of problems that are completely new. So we have not been able to solve them, I would like to present some of them. So the first part is the applications of the continuum variational methods, and I will focus on the simplest. Since I want to focus on methods, I've chosen the simplest model to think of. So it's the model when we have a spin system. So the nodes of the lattice, to each point of the node, to each node of the lattice, we associate an unknown, so the parameter ui, I is the level of the lattice, which may take two values. So we parameterizing in a different way. We always can think that these two values are real and are +1 and -1. And then we have pair interactions, so another simplification. Pair interactions, so the nodes interacting points, and then we are looking at the surface scaling. So we scale the energies so that we detect the presence of a surface. So this means that the energy density is the original energy density that is scaled by the lattice spacing, epsilon, to the n-1, so epsilon, when you have 2 dimension, epsilon squared in 3 dimensions. So. And we will make pictures, and for pictures we will stick to Z2 or a triangular lattice, but we can extend everything to more general lattices. So this is the picture that we will look like. We have values and the nodes, and we can color into different colors, and then we have interactions of each point with the other one. So already here we have 2 types of interactions. So we have what are called ferromagnetic. For ferromagnetic interactions, well, essentially we have 2 values, +1 and -1. So we can't have too many energies. Indeed, the energies can always be rewritten upon adding or multiplying our system by some constant as depending on a single parameter that we call sigma ij. And then the rest we normalize so that it's 0 when the value of the nodes are equal. So we can always write it like above. So if sigma ij are positive, so if interactions are positive, then this interaction is minimized, of course, if all the values are equal. So if you color our lattice with the same color. Well, otherwise, we have microstructure. Microstructure that can be very, very disordered for the triangular lattice, but also we can have ordered minimizers. So each of these triangles, the energy is minimized because we have two interactions that are happy and one which is not. We can't have all interactions happy. So maybe I spend time. So this is already a model of this is a model when we think of having simple interfaces. Here, where we have the interfaces are all over. So somehow already this allows us to play a little with our model. So we first focus on ferromagnetic interactions. So the first part will be all on ferromagnetic. So when we think of having interfaces concentrated, and so we have energies which may in general depend on epsilon, or just the scale of the state energy. So it is meaningful also where the sigma ij do not depend on epsilon, but are positive. So here is a little picture, and we think of so to minimize the energy, we would like to have all blacks or all whites. But this is not always possible because maybe we have boundary conditions or so. So locally, we think we will see some part which is happy at the minimum, some other part which is happy, and in between we have something interacting. So this is a very simple picture that everybody can grasp. And then we have some active interaction that may be colored in the different colors because they can depend on the orientation, on the fact that we have nearest neighbors or second neighbors next to nearest neighbors, and they can be weaker when we are. So let's look now. Let's introduce this epsilon and look from far away, a little far away. So again, there is no reason for interfaces to appear here. It's better to have them migrate there if they can. And so we expect something like this. So we have large portions of places where you have one color, and other large portions where you have the other color. And which means that here we expect that if we interpolate these functions, like taking the piecewise constant interpolation, we have some strong convergence. So here you have large zones where you have constants, and other large zones where you have constants. So this suggests the topology, the strong L1 topology, and suggests that in the limit we will have something. So if we let down epsilon go to 0, this is the picture that we expect here. Which means that, we think that locally we will have something regular. It's not a fractal locally, it's not something that replicates at all scales. We have something that looks like a straight line, and in a sense the energy will be uniformly distributed given the
Excuse me, I mean, all that should be strongly dependent on the boundary condition, right?
Yes, of course. No, we are looking locally. Then the boundary conditions are added, like always in gamma convergence. So we are looking what happens locally, knowing that, for some other reasons, then locally you have some percentage of white and black. So, how to prove that, until now there is no method. So what are the methods that we would like to use, or we are used to use, and would like to implement also in this Discrete-to-Continuum environment? So I mentioned in the static regime. So if we think that our system is driven by absolute minimization. So the main tool is gamma convergence, which is exactly a rephrasing of the fact of what we want to have. The minimum problems converge to minimum problems. So if you it's the convergence because it really implies what we want to, it's equivalent actually to what we want to prove. So that if minimum problems, minimum values and minimizer converge to minimum value and minimizer of the limit. Also, if we add some continuous perturbation, so we don't have something which is so depending on imposed forces, for example. So we have to change everything when we change our problem, or to some extent boundary data, but that's another problem. This is not a topological problem, but more a technical problem. So we have a tool. This is the first tool, gamma convergence, which is rather abstract. But then we want to recognize what happens in the limit. So again, the George comes to our rescue, and a lot of other people like Chocolate, Federer, many others, who have studied sets of finite perimeter. Now we have something which we expect converges to something, a system that converges to something which is on the continuum takes two values, 1 and -1, and we have an interface. So we can write down an energy on the interface, and indeed this energy is well defined on sets of finite perimeter. So from now on we will talk about this function u, or the set where this function takes one of the two values in the same way. So in the limit we have something which lives on functions or on sets, because we have characteristic functions. Okay. And there is a whole theory of surface energies which is derived from geometry measure theory tools, and actually Ambrosi and myself developed it in the early 90s, alas, long ago. So the first, so the basic question is, does there exist a limit surface energy? So now we have made no assumptions on our coefficient sigma and j. Is it sensible to expect for rather general systems to have a limit which is a surface energy? This problem was from the fact that it's not trivial issue. The first name of the list is Caffarelli, so we are in good company, and we studied from different standpoints, and the optimal theorem is in a sense this one. It says, okay, if the interactions decay sufficiently fast, we can make it better, but otherwise we have taken much more space. So if the interactions decay faster than one over the distance in the end is 1, and if you have coerciveness on the nearest neighbors, so you have positive interactions between nearest neighbors. Otherwise, you can have two different lattices going in different directions, if you want. And if what happens for far away interactions is really negligible, so we have a negligible long range effect, then there's always a limit surface energy, which also has some properties of being convex and positively homogeneous, being convex in the normal, so it means that oscillations are avoided in the limit, are not preferred in the limit when you extend it by positive one homogeneous. And I will skip the technical things. So we have so we always have a limit, and it's nice to picture to understand what the limit, how the limit is linked with the geometry at discrete level. For example, looking at Wolf shapes. Wolf shapes are minimizer of the perimeter given volume. So, and looking at Wolf shapes, you read somehow what happens at the discrete levels. For example, here it's a system of first and second neighbors, and the outcome is an octagon, which describes the most convenient directions are the coordinate and the 45 degrees directions, or simple, if you take just the nearest neighbors in square lattice, you get, as you expect, square. If you take a triangular lattice, as you expect, you obtain an hexagon. Then you can take inhomogeneous interactions that are maybe more stronger, I don't know, now in one direction, and you get something which may be irregular. But in general, you get something. If you have short range interaction, you always get a crystalline shape, so a polygon, but you get it by, if you take long range interaction, you can obtain really every shape. Okay? But it's interesting that, so this is a theory in which you have some hypotheses, and hypotheses are optimal, and if you some of the hypotheses fail, then you get something really, you get something more, something else. So, for example, if you remove the third hypothesis, so that you have a slow tail, so you still have something which has finite energies on interfaces, but you get some non-local addition, and also other even the periodicity can be relaxed. For example, you can take random lattices with some assumptions, or periodic lattices, aperiodic lattices, and even you can relax the ferromagnetic assumption, but replacing the fact that you can control the number of ground states. I would say I've taken the simplest case of having just 2 parameters. If you go to 3 parameters, already the situation also gets more involved. So because you have function defined now on partitions, because you have more than 2 sets, more than 2 labels, and this type of energies are much more complicated from the viewpoint of geometric measure theory. And even if you have only two ground states, so still -1, 1 are the minimizers, then you still can have some interesting effect from the third phase that can concentrate on the interface. These are what are called surfactants, and you have an energy style that depends also on the concentration of an additional phase here. And to some extent, you can extend also to positive temperature. This has been done by Ruckhaus and Tedeschi, even though not exactly for this kind of thing. For the static case, for the evolutionary case, we have some other tools again in which the geology was involved, but also it's a classical tool, an implicit Euler scheme, in which you can define an evolution by iterative minimization. So you start from, you fix a time scale, tau, you fix an initial datum, and then you produce a piecewise, a discrete in time evolution, which in this case is a discrete in time and space evolution, by minimizing the energy, which in this case also depends on epsilon, plus some dissipation term here. So this is a kind of minimizing this type of discretization of the time derivative. And this is and L2 in our case, in the case of sets or factor discrete functions, this is an L2 interfacial distance of the boundaries of the set. So you obtain a discrete in time and space in evolution, then you pass to the limit, and the limit, if everything is smooth, is in general theory describes a gradient flow of some limit, but in this case it's defined also if you have no differential structure. What is there is a connection with the static analysis, because as you see, we are minimizing something which is written as an energy plus a perturbation, and if this perturbation is continuous, then the theorem of gamma convergence says that you can approximate the first problem with the same problem related to the gamma limit. Okay? But only if you have so you have fixed tau. So if you let also tau vary, this means that you have to let tau go to 0, slowing up. So the description, this is a general theorem, so that for slow time the gamma limit already gives a description, but otherwise you have something, define maybe something different, which depends on the mutual way epsilon and tau go to 0. So an example, as we saw for nearest neighbor interactions on the square lattices, on the square lattice in 2 dimension we have the limit which is an energy which has minimizer squares. Okay, so this is a crystalline perimeter, and the evolution of this type of perimeter has been studied by Algren, Taylor-Wong, and especially Algren and Taylor. And the result is that squares and also rectangles move according to their crystalline curvature, which is the inverse of the length. So they shrink homothetically. So this happens also for spins, at least for slow. So this is an example. So now let's turn to the discreteness effects. I don't want to enter here, and I've not written mathematical details actually in many of these examples, because it's too technically demanding. But I'd say so. One of the good things of looking at discrete systems is that in discrete system they are inherently non-local. So you don't have a gradient, you have only different quotients, and for different quotients having interaction with nearest neighbors, second neighbors, 10th neighbors is the same. But from the standpoints of the continuum theories, this means that you are looking at interactions which can be interactions between different layers or of involving higher order effects and so on, all within the same type of theory. So with a little variation on the type of energies we have looked at, we can obtain multi-phase material surfactant, as we have seen, double corrosive media, a lot of problems which usually involve a lot of topological assumptions on the media and the continuum. For example, double corrosive problem can be stated only in 3 dimensions, because you can't have topological infinite connected components in 2 dimensions. Well, in the discrete setting, this is completely okay, it's completely normal, and you can have double corrosive media also in 1 dimension. So it's also a very nice a very nice environment in which to look at low-dimensional objects. So you can do dimensional reductions, has been done in the continuum, but in this direction, dimensional reductions, you can maintain the microscopic variables. For example, you have dependence on the chirality of some nanotubes, on the way the nanotubes wind around the axis, or on the number of layers of thin film, which are completely lost in continuum theories. While here you have surface effect or rigidity effect that are very strong in the discrete. Or you can model other types of environments like quasi-crystals that are typical in discrete setting and not in the continuum. And I would like to hint just at 2 or 3 problems that are easily set on the discrete. One is discrete optimal design problem. So you have a network and you want to describe all the possible structure, and especially the more extreme structures that you can obtain from within some design constraint. So this is a simple example that we're looking with Leonard Prof in the audience. The composite of 2 types of ferromagnetic interactions, where you want to describe all the possible limits when you mix 2 types of connections, if you want to looking at conducting networks. And in this case, we can give exact bound, which is surprising because in the continuum you cannot. And this is an illustration, a nice illustration, I think, of the difference of the freedom that you have on the discrete level. Because on the continuum, optimal microstructure obtained by layering. But layering optimizes some structure in one direction, but not in the other direction. Conductivity is higher in one direction, but it's lower in the other direction. So you have to make, you have a trade-off of this. While on the discrete, you can optimize structure in both directions. You can have, say, connection in series or in parallel in both directions. And so this is the way one can construct optimal microgeometries. For in the case of nearest neighbors, and we have even more surprising constructor for long-range interactions. That's one type of problem which is very exciting and new. Another problem which is not new but still very interesting is the one, the problem related with percolation. Now the problem is the same if you want, but now you are introducing some random variables, so you are choosing randomly the coefficients. So this is something which is harder and more abstract to picture on the continuum, while on the discrete level, this is a very natural environment. So you have, so you can think of a finite variable and then placing randomly 2 types of conductors or defects, if you want, and with probability q minus p, and we want to characterize the limit and prove that the limit almost surely depends only on the probability, and link with the percolation problems. So describe it with percolation formulas, and prove some percolation threshold appearing in extreme cases. So in extreme cases, we will have when alpha say is 0, so we have voids, or beta is infinity, so we have very stiff connections. Then you have above or below a certain threshold, the behavior is completely different. And this brings in the connection between energy and the geometry of percolation clusters. So these almost surely if you throw at random this connection, this will have some geometry and some random geometry, and the properties of the random geometry must be described in terms of minimal paths, minimal problems, which are not usually so well studied in the percolation community. So there is a very nice interactions that have been going on in the last few years to translate the problem, the technical problem that we face on the variational standpoint, to technical problem to be faced from the percolation percolation standpoint, and it brings new operational questions that are new to percolation people, and hopefully we've been trying to get them involved, not successfully until now, but some of them had some interest, so there's hope for the future. So for the evolution, what are the new features that are brought in the evolutionary framework? So we've seen that in the evolutionary framework, for slow times, well, what we have, for example, for nearest neighbor interactions on square lattice, you have square shrinking homothetically with a law which is consistent with the motion by mean curvature. So this is for low time. But for on the opposite, of course, if you have fast time, so if the principle is that you first let one of the two parameters go to 0, if you have fast time, you first let tau go to 0. So you have to know what happens when you have a system of 6 pins that evolve, that are separate one to each other. What they do? They stay where they are. There is no energy, whatever, that can move them. So they are completely pinned. So it's clear that you have something interesting here, meaning that you have, for fast time, you have something which is completely still. It stays like that forever. On the other time, you have something shrinking by crystalline curvature. And what you have in between, that there will be some critical time scale, so critical velocity of time, if you want, of the time scale tau, so that you have something in between. Or maybe there is some threshold, and you have something between some abrupt transition. No, in general, you have really some smooth transition, in a sense, from one state to the other. And so one problem is to find the critical time scale, which in this case is exactly epsilon equals to tau. And once you have the critical time scale, you want to know if you can describe something with an effective motion, and this is been done some time ago. And here you have something shrinking by discrete crystalline curvature. So here you have some integer part, so forget about the gamma. So you move by the integer part of the curve. So it means that you have a very large sample that will stay still, because for a very large cube, this will have a small curvature. And it will shrink only if you have a small enough. So you have a size effect. And you get also a lot of other nice consequences about this type of motion, which is new in a sense. We are looking at the ODE system of ODEs with this continuous second right hand side, and we have non-uniqueness and so on. One thing that one would think is that one could have something now depending on the gamma limit, because it's always something shrinking by curvature, but maybe with some discretization that only discretize time taking maybe integer part, but it's not. What you obtain is in general a complex homogenization problem for the velocities. So computing the velocity when even if you know the gamma limit, it's not a trivial task. So even we have some examples with Schiller in the audience again of energies convergence always to this crystalline perimeter, but such that the homogenized velocity is very complicated. There are many questions in general to ask about these problems with homogenized velocity. What about the third, late, but I'd like to hint something about the third topic, so new problems, and this come from the fact that so until now we have looked at ferromagnetic interactions where we expect the interface to localize, but we can have on the other hand if you have antiferromagnetic or mixtures of ferromagnetic and antiferromagnetic interactions, you have ground states, so minimizers, as we have seen, which have diffuse interfaces. So we have some lattice, typical lattice or non-typical lattice microstructure. It can be very disordered, as in the case of nearest neighbors on the triangular lattice, or can be very, very ordered and satisfying all the interactions, for example, on the square lattice, nearest neighbors on the square lattice, or you can have a complicated pattern of ground states depending on the type, on the strength of the interactions. For example, here, interesting cases where you have striped interactions. In these pictures, the red interactions are the interactions which are not at the minimum on minimizers. So these are all minimizers, but they don't minimize separately interactions, except in the last case. So one can ask the same questions, but the answers will not be the same, because can we now, before passing to the limit, we have to define the convergence. So can we describe the gamma limit? But before describing the gamma limit, what is the convergence? Do we expect some interfacial energy in some sense? Well, in some sense, we could expect, for example, in the third case, where you have ground states which are not frustrated. Locally, you see some disorder, if you want, order, but not of uniform type. But you will see some interface in which this order changes. So even though that here the interface is not of the type as before, going from black to white. It's going from white and black to black, but it's still of the same feature. So it concentrates on something. While in other cases, like the triangular case, you can have regular patterns that change into other regular patterns without paying any concentration. So it's not so obvious to see what are the relevant parameters in the limit. But we could still follow this the path of describing the limit in terms of surface energies if we can single out ground state, a finite number of ground states, and between these ground states you have an energy barrier. So this is the case in the picture before, where you single out two different ground states. Here they are not the same. So here this is white, black, black, white. Here is black, white, white, black. So these two are different, and they differ from a period. So they cannot be superposed continuously. So these are two different types of ground states, and if you want to pass from this to this, you have to have some interface in between. So there is an energy barrier. They look the same, but they are completely different. So you have to also to take into account the usual assumption, so that you have some K in the surface state decay, so not to have long range interactions. But then, okay, the statement is more complicated, but essentially it says that the ground states themselves are the parameters in the limit. So it means that locally, in the pictures before, if you have something with small energy locally, it will look like this, or like that. And there it's different, and in between there will be some interface. And if you have maybe 6 or 10 or 16 parameters, then locally you take one of these shapes of these patterns of parameters, and in between you will have some interface. So the limit will be automatically more complicated because you will be a functional defined sets of partitions which are of degree of complexity higher than the interface into interface. So for example, examples of this type of parameters, we have seen the striped parameters in the case of next nearest neighbors for antiferromagnetic interactions. So if you start even with antiferromagnetic interactions next to nearest neighbors interactions in the square lattice, you end up with 4 parameters, which are stripes. Stripes in the interface between them. If you take nearest neighbors antiferromagnetic, and you add a little ferromagnetic interactions, then you get hexagonal shapes in the triangular lattice, and these satisfy the having an interfacial energy between them. If you go to next nearest, so third neighbors interaction in the square lattice, you get 16 ground states which are striped patterns or checkerboards, and you always get some interaction with some surface energy going from one level. So this is a nice thing that you start with 2 parameters, plus and 1 minus 1, you can end up with 16, 32, 64. How many? Can you end up with 17 or 31? I don't think so, but that's you always get something like this. So this is and so this says that this implies the type of that we are not able to ask the same questions as before. So homogenization, can we ask what is the type of limit that we obtain mixing ferromagnetic and antiferromagnetic interactions? And it's not so clear. Because even if here are example where you mix ferromagnetic are with single line, and antiferromagnetic which are double line, with the same proportion. So with the same proportion you can get something which is non-frustrated, so you get interfaces, or you get something which is partially frustrated, means that you get interfaces in one direction but not in the other one, or you're totally frustrated, so you can get complete mixtures of ones and minus ones without following any fixed pattern. So here the pattern is very, very precise, stripes. Here the pattern is precise in one direction, but in the other one is free, so it's precise in these directions, it's white, like white. And here the pattern, there is no pattern at all. So you can give examples showing that you obtain a lot of energies in the limit, but it's not clear what are the general type of energies that you obtain. And this is very exciting, I think, because now the type of problems are different. The type of problems are so what are the types? What are the number of ground states? Not what is the type of energy. What is the type of ground states? The number of ground states, depending on the periodicity of the interactions, the percentage of the interactions. So something is still vague, even though we have some partial results that are combinatoric now problems, which are very complicated to state. We have 4 lines here to go through. Or you can rephrase the same thing in the probabilistic setting. So, for example, you can throw at random. This is a very hard problem, throwing at random ferromagnetic and antiferromagnetic. But so with this type of result that we are not going to read, you have some hope that at least if you move away from the probability 0 or 1 a little bit of having ferromagnetic or antiferromagnetic interaction, you still get only essentially two ground states. Okay. And okay, really, I don't have time to go through this, but I would say that another nice effect of antiferromagnetic interaction is the importance of boundary conditions. Boundary conditions have much more effect with for antiferromagnetic interactions, which, for example, here you have 2 examples of ferromagnetic, antiferromagnetic stripes, say, hitting the boundary, and the second has much less energy on the boundary than the first one. So you get in your description something that really depends on the orientation of the boundary. So the boundary is again another design variable. And when the boundary is very big, for example in thin films, the effects are really macroscopic if you want. For example, you have the number of ground states depend on the thickness of the film. So here you have triangular and first and second, sorry, your first and second neighbors antiferromagnetic, and the number of ground states depends on the thickness of the film. You start from 2 ground states, 4, and then you get 4, 6, and sometimes it's another example. It's not even monotonic. You get 6, then 8, then 6 back, and you stabilize by 6. And even if you have something which is completely frustrating, like a triangular lattice, of course, if you have a thin film, it's not. It's not, and the number of ground states increase exponentially. Just to conclude, the effect of the microstructure in moving boundaries is also is even more interesting. So because you have the effect of motion by creation of the facts, which adds up to the motion by mean curvature. So the interfaces move in different ways, depending if you are able or not to create some type of effects, or if you have some inclusions, then you can get. This is an example where you have some mixtures of strong and weak inclusion. You can get some motion in which you have an initial state that moves in, and these black dots are parts of your system that are left behind. This is some connections with some problems, fluid mechanics, of cooling of binary alloys, where you get something that cools faster in one of the components and slower in the other one. So you get these curly things that come out of a bulky part moving by motion by curvature. And finally, also the fact that we are free in discrete to consider problems that are not considered the continuum. For example, maximizing the perimeter. Maximizing the perimeter makes no sense in the continuum because you can have very weakly sets not convergence to a big sector. This is a way instead that was being suggested by John Kahn to us to define a nucleation and expansion of crystalline structure. And also this one has a lot of technical interesting connections, even with the problem in number theory, counting integers point inside the ball, which are very, very exciting. So I think I can conclude saying that, okay, I've given an overview of what we've done, and I hope to show you all interesting implications to consider discrete problems. Also, in this very, very simple case of having just two parameters, you've seen that we have a lot of consequences. Thank you very much.
Very good, thank you. So, there are questions? Remarks, comments?
Maybe it's because we adapted to deal with complex valued Braides interactions. So, for example, I have in mind the so-called tie binding models for electrons in a crystalline solid, and still you have a lattice structure and a dynamics which is governed by a sort of discrete Laplacian, but with complex optic terms which correspond to local magnetic fields in the crystal.
Then I don't know, but I hope so. I mean, I think that, I don't know if there are have something like that. But I'm not able to basically in this framework. You can discuss it.
Some other questions?
Just one question. Concerning the fact that with gamma convergence you can capture even the time behavior of a model if the time is sufficiently slow, I was wondering what do you mean by slow, if you can elaborate a bit.
Slow is an unknown slow.
Okay.
So it's just a diagonal thing. So you know that, so if you go back, you can also, so you have some parameter which is tau, which is fixed.
Okay.
And then you know that for each tau you have a gamma convergence sequence.
Yes.
And now you can choose tau as so slow that you get a diagonal sequence.
When compared to the velocity with which epsilon goes to zero.
Yes,
In
the
this
tau depends on epsilon.
Yeah.
Tau and epsilon go to zero at the same time. And you can choose the mutual dependence. Usually it's a dependence on tau and epsilon, or epsilon and tau, that is the discriminant.
And the specific convergence rate depends on the particular problems, I guess.
Of course, because every time you can recall, you can call epsilon, you can call it epsilon squared.
Yes.
So you can scale everything, and so it depends also on your parameterization of the problem, of course.
Okay.
And, but in this case, you can read that tau equals epsilon is the critical scaling.
Thank you.
No. Any other question?
I got another question about time evolution. So you told us that the time discretization is based on an implicit Euler scheme. Are there also other kind of time discretization that you use, or can be physically meaningful, or this is the typical way of increasing time?
I don't know if it's typical. Kind of from a variational standpoint, I don't see any other. So there are other type of discretization that I know, but more or less a variation of this. So you can have a continuous in time and discrete in space, or discrete in time, continuous in space approximation. But as grading flow in this generality is concerned, so this requires no differentiability, no just the semi-continuity of. So if you want to deal with problems which really So you want to define the gradient flow for problems which are not differentiable. So that's why you are using this type of approach. So if you have more structure, then I guess you can use.
So, there are other questions? So if not, let me ask you something a little bit outside. I mean, you assume the lattice all the time. What is known about the fact that if you just particle in the continuum and want to find if there are minimizing structure which creates a crystal or a lattice? Can you comment on that? There are results in this direction?
I think that there are many in a different. So you want to conversely to prove that there is the lattice. So somehow one type of question is crystallization, like chlorophorian tile has been doing.
I mean, but it got result in 3 dimensions or only 2 or...
In 3 dimension, if you add some 3-point interactions, and but I haven't seen really the paper published. And there are other type of like vortex displacements. You want to because of lattice. So you want to have something living on discrete particles and how they interact, they arrange, but you have a far field like interactions interacting with the continuum field, and there are results that they place in a triangular lattice. You see, this he was talking about that. I guess there are more.
You don't know another question. Let's